All right, so today for recitation, we'll do a couple more optimization problems, review both techniques from earlier this week. So the first question I got on Piazza was to talk about homework number 15 on homework 6. And so actually it is the same problem, or I guess on WebAssign it'll randomize some of the things, but it's basically the same exact problem as homework 4. The idea is that you're going to use the two different methods that we learned this chapter to do it. But this question is also kind of neat because, well, we learned 2 ways to do it earlier in this course. So I can think of 4 different ways we can solve this problem. And I figured it might as well be a good review to tie everything together. So let's see here. So old geometric approaches, of which there are 2. So anyway, we have our plane, right? We have our point. And if we want to get the shortest distance from the point to the plane, we know that that has to happen perpendicularly like this. So one way we could solve this problem is to set up the equation of the line through that point and perpendicular to this plane. So we'll use the normal vector of this plane, 1, 1, 1, as the direction vector for this red line. So the line through 2, 0, minus 3, that's perpendicular to the plane, will be given by x is, well, our point is 2, 0, minus 3, and then our normal vector, or our direction vector of the line is going to be 1, 1, 1, so x is 2 plus t, y is t, z is negative 3 plus t. And then we'll find the intersection point of the point of the line and the plane. Right? Because at the end of the day, the point that we're looking for to calculate distance between is going to be right there, that purple point on the plane. So to find that, we plug that into the plane equation to get that, well, x plus y plus z equals 3. So what is that? 3t equals 4. T is 4/3. And so then the intersection point is, well, 2 plus 4/3 is 10/3. And then 4/3, and then negative 3. So that's what, negative 5/3? Yeah. 4/3 minus 9/3 is negative 5/3. So that's our point. And so then the answer is distance 2, 0, minus 3. So the distance from that point to the point 10/3, 4/3, negative 5/3, which ends up being, well, I guess we kind of already figured this out on some level, but yeah, basically I did 4/3 squared plus 4/3 squared. So 10/3 minus 2 is 4/3. 4/3 minus 0 is 4/3. Negative 5/3 minus negative 3 is 4/3. So what is that? The square root of 16/3, which is 4 over the square root of 3. So you can set up the perpendicular line and then find the intersection point of that perpendicular line and then do the distance between those 2 purple points. That's one way to do it. Okay, well, what's another way to do it? we could use vector projections. And so there's that formula, distance point to plane, that you might have memorized. You could do that if you want. That's derived from this following idea. So I'll show you the idea of the vector projection just to refresh your memory. So we have 2, 0, minus 3. The idea is that, let's call this point P. If I pick any point Q on the plane, and I get the displacement vector QP, if I project that onto N, and so yeah, I shouldn't have, I'm going to correct this a little bit. I'm going to make this blue vector a little bit shorter. We didn't know that that was the exact length between those points. So anyway, yeah, this blue vector 1, 1, 1, that's our normal vector of the plane. This is the distance we're after. And so that's the absolute value of the scalar projection onto the normal vector of this displacement vector QP. So if I remember, the scalar projection can be positive or negative depending on if your vectors make an acute or obtuse angle, but we want distance to be a positive number, so we'll take the absolute value of the scalar projection. Okay, so now it's up to us to figure out what point we want to use on the plane. Anything works. So for example, x plus y plus z equals 3, I could use 3, 0, 0. That, of course, satisfies the equation. So this QP displacement vector is going to be negative 1, 0, negative 3. And so remembering our formula for scalar projection, it's the dot product over the length of the vector you're projecting onto. So we're doing the dot product of 1, 1, 1 and 1, 0, minus 1, 0, minus 3 all over the length of 1, 1, 1, which the dot product looks like it's negative 4. So the absolute value of negative 4, of course, is 4. And then in the denominator, we have square root 3 is the length of 1, 1, 1. And hey, what do you know? It's the same answer we got using our other approach. So that is good. Okay. And so that's our two geometric approaches. I don't think that's what the homework wanted you to do for either number 4 or number 15, but whatever, it's good to remember that you could do that if you want. So let's go over the calculus approaches that we learned about this chapter, this week. So as far as the calculus approaches go, we're trying to find the point closest to 2, 0, minus 3 on that plane, right? Because the idea is that this point's farther, that one's farther, this one's farther, this one's farther. So we're trying to minimize distance to 2, 0, minus 3, so that's how it becomes a calculus problem, minimizing distance. So we want to minimize distance to 2, 0, minus 3 for the points on the plane. And so something you might have noticed if you've tried some of these web homework questions or taken a look in the textbook, I think they do a couple examples like this. I don't think I discussed it on Tuesday. I sort of was going to wait for you guys to see it on the homework. But I guess for some quantity that's greater than or equal to 0, so for example, distance is what we're dealing with in this problem. Distance in this course, remember, we're not doing signed distance. Distance is always positive or 0. It's never negative. So for something that's non-negative, you know, squaring preserves order. For example, like if I had this list of, you know, 1, 2, 5, 4, 3. So if this is like D, and I look at the list of the square of these numbers, like the minimum of D is, well, if you just like look for the smallest number on these lists, clearly 1 and 1 are the smallest, and then 5 and 25 are the biggest. And so essentially squaring is a monotone function when you are doing it to non-negative values. So it preserves this optimization. So the way we could write that is that the minimum value of D, the minimum value of D squared is the minimum of D then squared. So if D were negative, it could screw this up. But since distance or D, whatever we're thinking of, if we're doing this for a non-negative quantity, the optimization and the squaring can be performed in either order. And I know I've mentioned in this class before, you gotta be careful when you're interchanging order. To be honest, I think a lot of the big important questions in math, are whether or not things care about the order in which you do them. And so some things do care the order in which you do them. For example, when you put your shoes on versus when you put your socks on, makes a difference which one you do first. But then other things don't make a difference if you put your right sock on first versus your left sock on first. Who cares? Once you've done both, you're in the same place. And so, yeah, this whole optimizing non-negative quantities and squaring, it turns out it doesn't care which order you do it in. And so essentially what we're going to do is instead of minimizing distance to 2, 0, 3, 2, 0, minus 3, we're going to minimize distance squared. Because if you remember, the distance formula has that annoying square root in it. And, you can do all this with the square root present, but, we're lazy. And my philosophy in life is the laziest correct way to do something is the best. And so let's just minimize distance squared. Instead of minimizing distance, we'll get the same point, we'll get the same result. Okay, so how are we going to set that up? So why can we deal with distance squared? That's what this little box is explaining. So anyway, we want to minimize, well, think about our distance formula, distance x, y, z to 2, 0, minus 3 squared. So that's going to be x minus 2 squared plus y minus 0 squared, so just y squared plus z plus 3 squared. Okay. 4 points on the plane, x plus y plus z equals 3. Okay, so the third approach I'm going to show you is when you set up as 2 variable unconstrained. And this is, I think, the process that when you did problem 4, that it walked you through. Okay. So how is that going to work? We're going to use the plane equation, and we're going to solve for z. So z is 3 minus x minus y. So we want to minimize capital F of xy, we'll call it, just in terms of xy. So x minus 2 squared plus y squared plus z plus 3 is 6 minus x minus y squared. And so the reason that this is unconstrained is that as far as x and y is concerned, you could pick any x and y value. That the plane goes on forever, any x and y value in R2 is fair game for the domain for this optimization. And so for unconstrained optimization, you're setting the x and y partials both equal to 0. So x partial, y partial, both equal to 0. Without too much trouble, you could move that 2 times 6 minus x minus y to the other side to get that, yeah, that x minus 2 equals 6 minus x minus y. That's what equation 1 is saying. But equation 2 is telling you that that's equal to y. So I divided everything by 2 just for simplicity. So y equals x minus 2. And then you kind of go from there. So when I post this, I will reorder these pages. So let's plug y equals x minus 2 back into equation 1. We get 2 times x minus 2 minus 2 times 6 minus x minus y. We said y was x minus 2 equals 0. So, okay, x minus 2 minus 8 minus 2x equals 0. So 3x equals 10. X is 10/3. And then y was x minus 2, which is going to be 4/3. And then z is 6 minus, well, at that stage, I guess we could just do, capital F of 10/3, 4/3 is x minus 2. So 4/3 squared plus y squared plus 6 minus x minus y squared. So that's what, 18 minus 10 minus 4 is 4/3. So 3 times 4/3 squared. And so distance is then the square root of f, because remember we were dealing with distance squared. And so, of course, we get 4 over square root of 3. As we were expecting. Okay. So that's the process. I think that when I was looking at WebAssign, it's one of those where you have to do multi-steps. So I'm pretty sure this is what you were walked through. Okay, and then the last approach, which I guess is what someone actually asked me on Piazza, was when you're doing problem 16 or 15, whatever it is, 15, you're told to do this process using Lagrange multipliers. So set up as 3 variable, 1 constraint, which, whatever, again, remember for quizzes and tests, we're only ever going to do 1 constraint. So I'll just call this 3 variable constrained and do Lagrange. So the way you would phrase this question would be minimize, we'll call it lowercase f. We're going to leave everything in terms of x, y, and z. We're not going to get rid of z. But then we're going to take care of the fact that we only want points on the plane by using that constraint. So subject to the constraint, x plus y plus z equals 3. So Lagrange for this is grad f is lambda grad g, and g equals k. And so this is the g of x, y, z, giving us our constraint. So grad f is that, and then grad g is 1, 1, 1. And then again, don't forget your constraint equation. Okay, and then so this one's not so bad. It looks like lambda has to be from equation 1. Well, I'll do lambda over 2 just to make things easier. Lambda over 2 has to be x minus 2 by equation 1, but by equation 2 that has to be y, and by equation 3 that has to be z plus 3. So, for example, y is x minus 2 and z is x minus 5. So we could substitute that into equation 4 to get x plus y plus z. Z is x minus 5 equals 3. So 3x equals 10. So x is 10/3. Y is 4/3. Z is 4/3 minus. Did I do this right? I'm thinking I screwed up. I think I'm getting a different z value than I was before. So z is x minus 5, so 4/3 minus 15/3 is negative 11/3. Huh. Okay, give me a second. Where did I screw up? No one's here to help me. Okay, I'm gonna pause this while I look. Okay, so I think I just got confused on, I was just trying to go too fast here. Z is x minus 5, 10/3 minus 15/3 is minus 5/3. That's what I was getting before. So I think I was doing y minus 5 and just getting the wrong thing. So anyway, those are our x, y, and z. And then f of 10/3, 4/3, negative 5/3, of course, is going to be then 3 times 4/3 squared, just like we saw before. And so then the distance is the square root of that. Because remember, we're dealing with distance squared, so 4 over square root of 3. And so that's the fourth different approach for this kind of thing. All right. So hopefully that clears that up. I think the tricky thing, probably the reason I got this question was for some of these you have to create the function you're trying to optimize on your own. I guess I did the example with the open top box a couple of times, but sometimes you're asked to do things involving distances. But yeah, so I figured I'll do one more, 2 different ways. We're not going to have any geometrical approach that'll work. So another pair of repeated problems that maybe the constants changed a very little bit, but otherwise they're pretty much the same exact problem, is if you look at problems 6 and 17. So find the points on the surface, y squared equals 1 plus xz, closest to the origin. So it turns out, let me think here. Through a rotation, this is, I believe this is a one-sheet hyperboloid. If you've taken Math 220, you probably were taught, you talked about rotation matrices, so that there's some transformation that I could rotate, around the y-axis by some amount to change this to like y squared equals 1 plus x squared minus z squared. So if x, y, and z are my rotated variables, I have something like that. Whenever we talked about quadric surfaces, we never had different variables multiplied together. The reason why is that with the appropriate coordinate rotation, you can get rid of that. So if I basically if I take the one-sheet hyperboloid and rotate it a little bit, I can get something that looks like that, but that's not so important. I mean, the only thing that's really important here is the fact that this isn't a plane, so I don't really have a good geometrical intuition for it. So not a plane, we don't know the geometrical situation. I mean, intuitively, distance is still going to happen when you're going perpendicularly, so I have some surface S, but then the idea is that I don't know the direction of this surface, and in fact, it changes depending on which point I'm talking about. And so it's the gradient of the equation giving the surface that's going to come into play, and that's actually what's going to come into play if we treat it like Lagrange multipliers. But anyway, you don't have to worry about any of this. I'm just sort of explaining why, we don't know the geometrical situation, so can only use calculus. But we don't have anything from previous chapters that explains the situation using projections or geometry or anything like that. So anyway, we got to use calculus. And so basically we're going to set it up pretty similar to before. We want to minimize a distance xyz to 0, 0, 0 squared, which is, of course, x squared plus y squared plus z squared, for points on y squared equals 1 plus xz. So the first method, the way you did it for problem 6, was to write it as, and you could get rid of any variable, but notice, since the surface is given y squared in terms of x and z, it's most convenient to just deal with y squared. So it's substitute in that y squared is 1 plus xz. So distance to origin purely in terms of x and z we'll be doing this unconstrained two-variable optimization. Which means that we're going to set both the x and the z partial derivatives to 0. So I get 2x plus z, and then I get x plus 2z. And this, you go through and solve that z is negative 2x, and then you use that, and then you'll get that, what, like negative 5x equals 0 when you substitute in. But yeah, the only solution to this 2 by 2 linear system is x and z are both 0. And then using y squared equals 1, we would get, or 1 plus xz. If both x and z are 0, you get the points 0 plus minus 1, 0. And they're both 1 away from the origin. And I guess if you investigate it using GeoGebra or thought about it, for example, I could, if x and z are both 1,000,000, then y could be basically the square root of 1,000,000,001. Like, this surface goes on forever. So it makes sense that you can find points as far away from the origin as you like. So there is no there's no point farthest from the origin on this surface. So you can assume that then these 2 points that we get are the minimums. Okay, and then as far as doing it on number 17, so again, I'll reorder these slides when I go to post it. Fix that. So when you do it for problem, what was it? 6 and 17. So homework. Homework 17. You would do it as minimize. I'll call it lowercase f of x, y, z is x squared plus y squared plus z squared, subject to And I'm going to rewrite the equation slightly, because remember, our constraint has to be of the form g of x, y, z equals k. So you have to have all your x's, y's, and z's on the same side. We've had to do that several times throughout this course, so just be aware of that. And so yeah, this is a 3-variable constrained treatment of this problem. So we'll do grad f is lambda grad g, and g equals k. Gives us, well, grad f and then grad g is what? Well, the x partial is minus z. The y partial is 2y, and then the x partial is minus x. Sorry, the z partial is minus x, and then don't forget our constraint. Okay. So what do we have going on here? I'd like to solve for lambda in the first equation, let's say. And so let's assume that, so the first equation, if z is 0 and x is 0, okay, so yeah. Let's look at the case if z is 0 or non-zero. So if z is 0, equation 1 tells you that x has to be 0, and then equation 4 tells you that y has to be plus or minus 1. So what's the other possibility? The other possibility, if z is not 0, then equation 1 tells you that lambda has to be minus 2x over z. And then similarly, let's say that if x is 0 versus x not equal to 0, if x is 0, equation 3 tells you that z is 0, and then we're left with the same thing, y is plus or minus 1. So yeah, if either x or z is 0, it forces the other to be 0, which forces y to be plus or minus 1. So really, let's just see what happens if both are non-zero. If x is non-zero, then equation 3 tells me that lambda is 2z over minus x. And so if I put these together, I get that minus 2x over z is minus 2z over x. So x squared is z squared. And so z is plus or minus x. And then it turns out that if you look at the last equation, yeah, so z is plus or minus x. Did I do this right? Okay. Huh. I feel like I'm making this trickier than it has to be. So I guess I could get through all this, but actually, let me just scratch this. So, and then my reasoning is, and the trap I fell into, just deal with the simplest equation first. So yeah, sorry about this. Forgot the ideal order to do this in. So you can kind of see the trickiness of nonlinear systems, that it can get pretty complicated, the steps and things like that. So yeah, we should use the simplest equation first. So what is the simplest equation? It's equation 2 because it's the only one that only has two things in it. So first one has xz lambda, third one has xz lambda, third one has xyz. But notice equation 2 only has y and lambda. So I think that's sort of the easiest way to go. So the second equation I could rewrite and be careful is 2y minus lambda 2y is 0. So 2y times 1 minus lambda is 0. So y equals 0 or lambda equals 1. Okay. Well, if y is 0, that implies from equation 4 that x and z can't be 0. Because if y and either x or z were 0, 0 would be 1, which is impossible. So if y is 0, neither x nor z could be 0. So at that stage, then you could do the whole lambda from equation 1 is negative 2x over z, and from equation 3 is negative 2z over x, which then those together tell you that x squared is z squared. So z is plus minus x. Equation 4, since y is 0, is going to read that minus xz is 1. So essentially, z has to be minus x, because if x and z had the same sign, that wouldn't work out. And so you end up getting 1, 0, minus 1, and 0, I'm sorry, minus 1, 0, 1. Okay. Yeah, this is definitely an easier way of organizing it. So yeah, my rule of thumb, look at the simplest equation first. I should have done that because the second equation was the only one with two variables only, y and lambda. Okay, and then if lambda is 1, that's going to lead to the same answers we got on the previous technique. Because if lambda is 1, equation 1 tells us that 2x equals minus z. Equation 3 tells us that 2z is minus x, and then so it turns out the only solution to that system is both x and z is 0. Just do substitution or elimination. It's up to you. Which then means that y has to be plus minus 1. So we get 0, 1, 0. It's 0, minus 1, 0. And then these are distance square root of 2 from the origin. These are distance 1. So this then you would assume is the minimum. Okay. So yeah, sorry about that. I apologize. I broke my own rule of thumb. Deal with the simplest equation first. But that's the idea. So hopefully that really reinforces your different approaches, that you could convert between a 3-variable constrained to a 2-variable unconstrained. So unconstrained, you're setting the gradient equal to the 0 vector. Constrained, you're doing parallel gradients and using Lagrange multipliers. So anyway, I think those are all the questions I had planned for today. And yeah, so good luck on everything. And for 231 people, 230 people, I'll see you next week.